start the 5th week of this course. During this week, we will talk about crystal systems, point groups and space groups. And in the first lecture, I will talk about crystal systems. This will continue into the second lecture, and I will try to show how we understand crystal systems from the perspective of symmetry. So, week 5 lecture 1 will be on crystal systems. Okay. Now, let us talk about the classification of crystals. Okay. So we often say that a crystal can be thought of as a lattice plus a motif. What we mean is that you have a lattice which is an ordered set of points, and in those points, at each point you put a motif, and the motif might be a single atom, might be a few atoms, might be a collection of atoms, and so on. Okay. And now, if you just look at the lattice, okay, then the lattice might have very different symmetry properties than the crystal itself. Okay, so what is important is that crystal and lattice may have very different symmetries. Okay. And when we are talking about symmetry, we are really talking about symmetry operations, okay, in terms of operations, in terms of the symmetry operations like the rotations, reflections, and so on. Okay. And now, and the motif will have its own symmetry associated with it. So, each motif will have some sort of symmetry associated with it. Okay. Now, with this idea, what we realize is that the way we classify symmetry depends on whether we are looking at the lattice, the motif, or the entire crystal. Okay. Now, we can alternatively think of the crystal in a slightly different way. We can think of it as crystal consists of an asymmetric unit plus space group. Okay. Now, the space group looks at all symmetries of a crystal, all symmetries. Okay, so it looks at all the symmetries of the crystal, and so if you know the asymmetric unit, okay, then by all these symmetry operations you can generate the entire crystal. Okay, and remember, it also includes translational symmetry. So you can generate the entire set of symmetries of the crystal. Okay. Now, we already saw that crystals have both a point symmetry and a space symmetry. The space symmetry refers to the operations that involve translation in addition to the operations of a point symmetry. Okay. So what is important is that space symmetry includes point symmetry, and additional translation operations. Okay. So, if you just had point symmetry, okay, then typically you won't have the elements of space symmetry, so you won't have the translational symmetry elements. So, that also explains why point symmetry is used for molecules. It is also used for crystals, but if you have isolated molecules, okay, then we use only point symmetry and no space symmetry. Okay. So, space symmetry is not used for molecules, it is not used for molecules. Okay. So, you cannot use space symmetry for molecules. So, the point symmetry is the space symmetry minus those translational symmetry elements. Okay. So, now we can think of crystals in two different ways. We can think of them as a lattice plus a motif, or an asymmetric unit plus a space group. Okay. And the second characterization is based on the symmetries of the crystal. Okay. Now, one of the things is that both point symmetry operations. So, we have this operations. Okay, this the entire set. So, the entire set of point symmetry operations, okay, forms a group. Okay. Now, group is a mathematical object. Okay. So, group is a mathematical object, mathematical, we should say it is really a mathematical structure. Okay. So, what do we mean by something forms a group? Okay. So, what that means is that if you take a product of two point symmetries. Okay. So, suppose you have a point symmetry operation A. Okay. So, A is one point symmetry. And then you take a product. Okay, I will write a minus sign. Okay, that means, and B is also a point symmetry. Okay. So, this will give you another object C, which will also be a point symmetry. Okay. So, so if you have a set of objects, okay, such that you take a product of any of those two and you get another member of the object, then that is one of the properties for that set of objects to form a group. Okay. So, what we will show is that the set of all, and the word all is very important, all symmetry operations form a group. Whether you take point symmetry operations, you get point group, which is only involves point symmetry operations, and space group if you have point and space symmetry operations. Okay. So, there are certain other properties. So, we have already seen the product. The other property is that there is one element called the identity, okay, which is which we can denote as either 1 or E, such that 1 times A equal to A for all the elements of the group. Okay. So, you take 1 times A, you get A, and this is same as A times 1. Okay. That means you take your crystal, you operate it by the identity operation, and then you operate it by A. That is the same as operating it just by A. Okay. So, this 1 is called the identity element, and 1 is part of the group. Okay. So, 1 is contained in your group, and similarly there should be an inverse element. So, suppose you have A, then you should have A inverse such that A inverse into A is equal to A into A inverse equal to identity. Okay. So, what is important is that you should have, so group consists of a set of elements, okay, and these elements are your symmetry operations. Okay, these are your symmetry operations. Okay, such that if A and B Okay, let me call this group G, set of elements G. If A and B are a part of G, then A into B is also a part of G. Okay, so this symbol epsilon means it is contained in G. Okay, that means you multiply any two elements, you will get another element. And so this is the first condition. Second one, there exists an identity element contained in G. So, identity element. So, the identity symmetry is also a symmetry operation where you do nothing, and this has to be part of the symmetry group. So, the symmetry group, the set of all symmetry operations will include the identity operations, okay, such that A times 1 is equal to A. Okay, A times 1 is also equal to 1 times A. And the third one is that for all A that is contained in G. So, for any element of G, so any operation you can have an inverse operation. Okay, there exists A inverse, which is also a part of G, such that A inverse is equal to identity, and A inverse is also equal to A inverse A. So, A inverse into A is identity, and let us remind ourselves again that the product of symmetry operations means successively you apply one symmetry followed by the other. So, A multiplied by B means you first operate by B and then by A. Okay. So, keep that in mind. Okay. So, A times B means successive operations. Symmetry operations. Okay, that is to be kept in mind. Now let us go to the point group and space group. Okay, so what we said is that the set of all point. Okay, the word all is important here. All point symmetry elements. Okay. This is the set is called a point group, and remember identity is also a point symmetry operations. Okay, so keep in mind that this includes identity. Okay, so this is what is called the point group. Okay, and the set of all. Now, we have point and space, okay, or you could think of and I will say translational symmetry elements. This is called a space group. So, so if you take the set of all point and translational symmetry elements, then you get something called a space group. Okay. Now, what is important is that every crystal, so each and every crystal belongs to one space group and one point group. So, that means for each crystal you can identify what is the point group and what is the space group. Okay. And the other point I want to make is that the total number of point groups in crystals is 32 point groups. Total number of space groups is 230. Okay, so obviously you can have a space group and you can have one or more translationals. A space group consists of a point group plus translational symmetry elements. Okay, so you can have many more space groups than point groups. Okay, and the other terminology that is often used is that these 32 point groups are called as crystal classes. They are just called crystal classes. This is just a notation. Okay, so you can think of every crystal will belong to one of 32 crystal classes and one of 230 space groups. Okay. Now you can see that if you want to identify a crystal, okay, you give the asymmetric unit. So remember we said a crystal is equal to 1 of 230 space groups plus asymmetric units. That means based so the 230 space groups, one of the 230 space groups will tell you what are the symmetries, and then you tell what is the asymmetric unit, then you can exactly identify the crystal. Okay. So this is a different way of looking at the crystal as opposed to a lattice and a basis. Okay, and this clearly tells what are the symmetries of it, of the crystal. Okay. Now one of the things is we have learned that there are 7 crystal systems. Okay, and we said that we think of them in terms of the shapes of the unit cell and the restrictions on the shapes. Okay, but there is an alternate way to think of the 7 crystal systems in terms of symmetries. Okay, so I will list the first 4 here. So suppose you take a triclinic system. Okay, so what we are looking at is the essential symmetry. Okay. So we are asking the question, what is the essential symmetry a crystal needs to satisfy in order to be called a triclinic? Okay. And the answer is none, it need not satisfy any symmetry. Okay. What is the essential symmetry a crystal needs to satisfy in order to be called a monoclinic crystal? It should have one two-fold axis or a mirror plane. Okay. Now you might remember this, that the triclinic we have all these angles were different, and all these we had this unit cell shape where the lengths and angles were all different. Okay. And this was our triclinic system where all the lengths and angles were different, all this A, B, C, alpha, beta, gamma were all different from each other. So that was a general triclinic system, and there is no symmetry that it has to satisfy. Okay. No essential symmetry that it has to satisfy. Of course, since it is a crystal, it should have a unit cell, it should have the translational symmetry of a crystal, but other than that there is no essential symmetry that has to be satisfied to call a crystal a triclinic, to say that a crystal is part of a triclinic system. Okay. What about monoclinic? Monoclinic, we said that it should have one two-fold axis or a mirror plane, and if you remember the monoclinic crystal, okay, it had the restriction that 2 of the angles were 90 degrees, okay, even though the sides could be arbitrarily different. Okay. So what we had was that so you had something like this, this was 90 degrees, okay, and you had some other angle which was not 90 degrees. Okay. So basically two of the 3 angles were 90 degrees and one of them was not 90 degrees, and this shape of the unit cell, again there was no restriction on A, B, C. Okay. And the essential symmetry is that it should have one two-fold axis or a mirror plane. Then there were 2 trigonal systems. Okay. Trigonal systems are characterized by a 3-fold axis okay, and we'll look at the exact conditions on the threefold on the trigonal systems, okay. But just to brief, I mean the two trigonal systems, one was the case where you had a centered one and you had one that was not centered, okay, and each of them have one threefold axis, okay. The next one was the hexagonal system, okay. This had one six-fold axis, okay. Again, I won't go into this in detail, but we have seen the hexagonal system many times, okay. Similarly, the orthorhombic is characterized by three mirror planes or three two-fold axes, okay. So the orthorhombic system, the essential symmetry is that it should contain three mirror planes or three two-fold axes. The tetragonal system, the essential symmetry is one four-fold axis. Similarly, the cubic system has four three-fold axes, okay. And remember this when we think of our cubic system, we think that there are a lot more axes. There are four three-fold axes, there are three two-fold axes, and so on, okay. But the essential symmetry to call something a cube is the existence of four of these three-fold axes. So there are four of these three-fold axes, and that is what defines the system as cubic. Similarly, the essential system for tetragonal system is that it should have one four-fold axis. It should have only one four-fold axis. It should have one four-fold axis. Any system that has a four-fold axis falls under it can be a tetragonal system. So what you see is that as you go, cubic is the highest symmetry. It has four three-fold axis, okay. Then you keep lowering the symmetry, okay. And I mean hexagonal has a six-fold axis, which is slightly different from the others, okay. But you find that you could a tetragonal, if it has one four-fold axis, in addition it could have four three-fold axis, okay. So a cube can also be a tetragonal system, okay. So the existence of four three-fold axis is the highest symmetry, and that is a cube, okay. Now you could have one four-fold axis, okay, and that is sufficient to be called a tetragonal system. All right. Now we will see that this sort of way of looking at crystal systems is actually quite efficient, and this helps us identify the space groups. Let me emphasize once again that the essential symmetry, okay, is basically what is essential, okay. And if you so for triclinic, nothing is essential, okay. That means it could have a two-fold axis, it could have some other symmetries, but it is not essential to call it a triclinic system, okay. Similarly, for monoclinic, one two-fold axis or mirror plane is essential. It could have several other symmetries, okay. So what is important is that these are essential symmetries, and you know, crystals can have additional symmetries. Okay. So and what you also see is, I mean this way of defining a cubic system, it makes it very compact. So the definition is very compact. Any crystal system that has four three-fold axis is a cubic system, okay. If you have a crystal system that has a four cubic axis, it is a four three-fold axis, then it is a cubic system. So really it is a very terse and very short description of the various systems, okay. And this is what will be used to identify crystals. So I will conclude this discussion on crystal systems. In the next lecture, we will look at this in a little more detail. We will look at both the crystal system and the shapes of the unit cells, and we will try to correlate both these ideas. Thank you.